Hello and welcome back. Let's finish up this question that we were just looking at. We flipped 2 quarters 100 times, one lands 49 times heads, one lands 53 times heads. So the question is, would we believe that they always, or their proportion of landing heads is just going to be different in general? Well, 49 is pretty close to 53 when we think about flipping a coin 100 times. And after doing all of our work, we found that we rejected our hypothesis that we failed to reject our null hypothesis that the two proportions are going to be equal to one another. So our conclusion is that there isn't enough evidence to conclude the two proportions are different. So it would be fairly safe to say that the two proportions are probably going to be equal, but maybe more testing should be done. So the way that we had done this first one is we found the p-value, which is essentially the probability that we got those specific numbers of heads flipped, given that their proportions are equal to one another. So this is just seeing how likely this is. Another way to test proportions is to use confidence intervals. So we're essentially testing whether or not P1, the proportion for quarter 1 is equal to the proportion for quarter 2. And if they are equal, that means that P1 minus P2 is equal to 0. But what we can do is we can create a confidence interval for the range of values that would be likely for P1 minus P2. And if our confidence intervals contains 0, then we are confident that P1 minus P2 could be 0. Again, when we have a confidence interval, we have a range of values that P1 minus P2, P1 minus P2 could be in here somewhere. And if 0 is one of those, well, P1 minus P2 could be 0. So it's pretty likely that P1 is equal to P2, and we can't reject the null hypothesis that P1 is equal to P2. But if 0 were out here, that would mean that we're confident that P1 minus P2 is in fact not 0. And if we can confidently say that it's not 0, that means that P1 shouldn't be equal to P2. And we can reject the null hypothesis that P1 is equal to P2. So using confidence intervals to test hypotheses, essentially what we do is we're creating a confidence interval for the difference of the parameters of the proportions, and then whether or not 0 is going to be contained in that confidence interval. One thing that's important to keep in mind is that the confidence level is maybe a little bit tricky at times, and it's just something that you'll have to remember. For a two-tailed test, if we're testing that P1 is not equal to P2, there's two ways that P1 could not be equal to P2. P1 could be a lot less than P2, or P1 could be a lot more than P2. And when we have a significance level equal to alpha, for a two-tailed test, half of alpha is going to be on one side, and half of alpha is going to be on the other side. So our confidence interval is going to be, our confidence level is going to be the sum of those two areas. So our confidence level is going to be 1 minus alpha. So we've got 1 minus alpha is the area in here. In a one-tailed test, this is slightly different. if we're testing P1 minus P2, so if this is our alternative hypothesis, that means that if P1 minus P2, that means that we're looking at an area down here. If P1 is greater than P2, that means that we're looking at an area up here. So again, this is our significance level. So this right here is alpha, and this right here is alpha. But when we're creating a confidence interval, what we're doing is we're only taking a little bit in the middle, right? And we want it to be balanced. We want it to have the same thing on both sides. So we also have an alpha up here and an alpha down here. So the area in the middle is going to be 1 minus 2 alpha. And this is going to be a little bit strange, but essentially what we have to do is recognize, are we doing a two-tailed test? In which case we know what the confidence level is. If we're doing a one-tailed test, I didn't spell tailed correctly, one-tailed test, our confidence level isn't just 1 minus the significance level, it's 1 minus 2 times the significance level. So let's run back through our question and calculate our confidence intervals. We have some formulas for the confidence intervals. Essentially, what we're doing is we're taking, let's circle some things. We have P1 minus P2, as in P1 hat minus P2 hat. This is our sample difference in the two proportions. And this is what we would expect our entire population, our two population proportions, to be equal to. However, the sample could be wrong by a little bit. Maybe we didn't take a very good sample, maybe it's not very representative. So what we do is we subtract a little bit and add a little bit, and we give ourselves a range for the difference in proportions. So this little bit that we add or subtract is called the error, and it's given by this formula. It depends on P1 hat, Q1 hat, P2 hat, Q2 hat, the size of our two proportions, and Z. So this is the same as constructing confidence intervals from a couple of chapters ago, but I'll run through finding that Z score in this example. So let's remind ourselves what the example was. We flipped two coins, two quarters. One came up 49 heads out of 100 flips. The other one came up 54 heads out of 100 flips. And the alternative, the null and alternative hypotheses, the null hypothesis was that the two proportions are equal to one another, and the alternative hypothesis is that they are not equal to one another. So right away we know that this is a two-tailed test. And we know all of our sample proportions, our sample sizes. So what's left is just to construct our confidence interval. So we know P1, P2. We have to figure out E, and we've got a nice formula for E. So all we need to do is find our Z score. And this, I think, is simple to draw a picture. So again, we have a two-tailed test, which means that we want to construct a confidence interval for this intersection here. Our significance level is 0.1, so alpha is equal to 0.1, which means that we want to split alpha into 2 on both sides, so that our confidence interval is going to be 1 minus alpha in the middle. Alpha over 2 is going to be 0.05. So the area to the left and the area to the right is going to be 0.05. So if I come back to StatCrunch, and I know that the area to the left down here is going to be 0.05, that means our z-score, which this should look like a familiar number, is going to be 1.645. once I round it. So let's come back. Oops. So the alpha over 2 is going to be 1.645. Again, it's the z-score corresponding to the point at which below it is going to be 0.5, or again, above that point is going to be sort of a 5% probability, of 0.05. And we get the same z-score if we're looking up here to the right or down here to the left. So everything's symmetrical, so everything's nice. And then it's just a matter of plugging everything into our formula. So E is going to be 1.645 square root of, and then it's P1 hat Q1 hat over N1, P2 hat Q2 hat over N2. So P1 was 0.49, Q1 is 0.51 divided by 100 flips, plus is 0.54 is 54 heads versus 46 tails divided by 100. And if we do this calculation, we get 0.116. So now we need to construct our confidence interval, which is going to be P1 minus P2. It's going to be less than P1 hat minus P2 hat minus E, and the difference in the samples plus E. And plugging all this in means that P1 minus P2 is going to be somewhere between 0.066 and negative 0.166. So here's our confidence interval. So if we draw a picture, there's negative 0.166. Here is 0.066. 0 is in between there. So somewhere in between, somewhere in our confidence interval is 0, which means that P1 minus P2 could be 0. It's somewhere in between, we don't know exactly where, but it could be 0. So since P1 minus P2 could be 0, this means that P1 equal to P2 is possible. So we fail to reject. Because we can't reject our null hypothesis. So the last thing that I want to do really quickly is come back to StatCrunch and show you exactly how to do these calculations in StatCrunch, and I'll do another example in the next video. But if we come to statistics, we are looking at proportions, and we are using 2 samples, and maybe my face is in the way slightly, and what we have is a summary of the data. So for instance, we know that we had for one quarter we had 49 successes out of 100 flips. For the other quarter, we knew that we had 54 heads out of 100 flips. And everything is set up here for the hypothesis test for P1 minus P2 to be equal to 0, as in P1 is equal to P2, they're the same number. And our alternative hypothesis was that they are, in fact, not equal to one another. And that's it. We can simply compute this. And we get the same p-value that we had before, up to some rounding, because I had rounded a little bit funny. And this p-value is certainly bigger than 0.1, so we fail to reject. Perfect. The other thing that we can do, if we come back to stat, we can come back to proportion stat. We have 2 samples with a summary of our data. We had 49 out of 100 heads and 54 out of 100 heads. Our confidence interval, our confidence level is going to be 1 minus our significance level. So that's a 90%. And if we compute that, we get the same lower and upper limit